So we're going to start with a definition of a differential one form. Let's just define it formally without the abstract notion of differential one form mapping points in Rn to a linear transformation of Rn into R. That's like a more abstract definition. But for our concerns, if we have a one form on Rn, it's always going to look like some function of position times dx1 plus another component, so it's some function of position times dx2, and so on. So for example, this is a one form on R2. And what we're interested in is doing integrals over paths or contours. So we can define that as being some function from a interval of the real number line into Rn. We're going to also assume it's a smooth curve. So you can imagine that, right, we have this interval from A to B, and then we have n-dimensional Euclidean space. And we're going to, when, let's say, gamma at A gives you some position in Rn, and then as, let's say, T goes from A to B, we get different points in Rn until we get to gamma of B. So gamma maps this interval on the real numbers into some smooth path. There's a tangent always exists in Rn, and we want to define an integral of a one form over that path. Okay. Now, form, I guess this really means is that we're going to evaluate gamma at, our one form at points along the curve, acting on the tangent vector, or velocity vector. And this is defined, and that's neither here or there, I guess. What we really mean is that this is the one form evaluated at gamma of t. So that would be like gamma of t has components, n of them. Gamma 1 gives you the first component, gamma 2 gives you the second component, and so on. Okay, so what we're doing is, how can we write this? Well, we're using this kind of generalized omega here, right? So you would get the integral as t goes from A to B, and then this is really a sum. So I'll use the summation symbol. AI at gamma of t. And if x1 is given by gamma at t, then the differential dx1 is gamma prime at t dt. So the differential of the ith coordinate is just gamma, the derivative of the ith coordinate of gamma times dt. So this would be gamma prime of the ith coordinate component of gamma prime times dt. Okay. So for example, if it happens that gamma of t is t, let's say t squared, as t goes from 0 to 1. And so we're mapping the interval from 0 to 1 and the real numbers into some path where we see that y is equal to x squared, so that would be something like this. So gamma at 0 is 0, 0, and we follow this parabola until we end up at gamma of 1, which is the point 1, 1 in the xy plane. And here we have omega, a one form defined on R2. Make sure my audio notifications are up. Right, and we want to do an integral over this contour of our one form. So this is, by definition, the integral of x squared y dx plus y cubed x dy for a gamma. But once we have a parametrization for our path, then we can just use the bounds for the parameter for the path, so 0 to 1. And we see that x is equal to t. Let me write that out. X is t on this path, but y is t squared. And now you also want to compute the differential. So if x equals t, dx will be equal to dt. And if y is t squared, dy would be 2t squared 2t dt. Just the derivative of y times dt. So here we get x squared times y. So x is t, y is t squared, and then dx is just dt. Plus y cubed, y is equal to t squared, times x, where x is t, and dy is 2t dt. So you've essentially pulled this back to be just a regular variable of integral of one variable. And so let's see, t to the 6, t to the 7, t to the 8. Okay, so we get a fifth plus 2 nines, whatever that is, right? 19 over 45. All right. Now, we also want to look at the special one forms. These special one forms are born out of finding the total differential of a real valued function, a differentiable, obviously, function. Some one forms are born from being a total differential of a function. So that is to say, there's some real valued function f that's differentiable. And if you compute the total differential, what you get is the derivative of f with respect to the first coordinate times dx1 plus the derivative of f with respect to the second coordinate dx2 and so on. You notice that this is indeed a one form on Rn. So for example, let's use, suppose f is a real valued function on R3 given by x squared, x cubed, something really cheesy, y squared and z, yeah? So if we compute the total differential now, differentiate f with respect to x times dx plus differentiate f with respect to y dy plus the derivative of our function with respect to z dz. So this is a one form on R3. Okay. Now, what's special about these kind of one forms? Because not all one forms come from finding a total differential of a real value function. So what's special about these? In short, the fundamental theorem of calculus, but for line integrals. But let's see. If I want to integrate over some path from A to B to Rn, and I'm differentiating this one form, which you get from finding the total differential of f. Okay. So one thing you can think of is that this is the anti-differential over differential. They kind of annihilate each other, and you would just get f. And the fundamental theorem of calculus will tell you that you would evaluate f at the terminal point of your path, so gamma at b, and then minus the f at gamma at the starting point, so gamma of a. And we can kind of demonstrate this here with our example. Suppose that we have a suppose we use this differential. So then we would have, and gamma of t would have 3 components because we have a one form on R3. So here the first term would be 3 times x, but evaluated along our path. Let's just write that as gamma 1 squared, and y, gamma 2 squared, and z, gamma 3. Okay. And what is z? I'm sorry, what is dx? Well, if x is gamma 1, then dx would be the the differential gamma 1 prime dt. Plus, and then we have the next term, and dy would just be gamma 2 prime dt. And then we have the last term here, so we have x cubed becomes gamma 1 cubed, y squared, gamma 2 squared, and dz is just gamma 3 prime dt, as t goes from A to B. So what we want to notice here, somehow messed that copy, that we can first of all take out the dt, just factor it out, that's what I meant. And also note that this is really the result of a triple product rule. This is really the result of differentiating gamma 1 cubed, gamma 2 cubed, squared, gamma 3. Right here, so the derivative of the first factor with respect to t would be 3 gamma 1 squared, and then chain rule gives you gamma prime. The derivative of the next factor with respect to t, that would give you 2 gamma 2 times gamma prime 2, chain rule. And the derivative, the last factor, is just gamma 3 prime. Okay. So we see that, if you'd like, the anti-differential undoes the differential, and then we can just plug in the points. And indeed, we have gamma 1 cubed at the term at b, and so on. So I'm plugging in the upper bound. And then minus, this is from one variable calculus, right? The result at the lower bound. So we never want to do this again. But this is exactly your function f at the terminal point, minus f at the starting point. Okay. And this result, well, one of the manifestations here of the result is called the fundamental theorem of calculus for line integrals. Okay. And as a consequence, notice that the line integral only depends on the starting and ending point of the path. It doesn't actually care about the path you take from starting to ending point. So the integrals from gamma of a, all the integrals from, let's say, x1 to x2, regardless of the path, as long as you have the same starting point and ending point, which would always just be the function, the real value function f at the terminal point minus the starting point. So fundamental theorem of calculus. And that would be the same even if you took a different path. Call it gamma prime. Don't call it gamma prime. Call it C. The path doesn't matter, just the starting and ending point does. Another corollary to this is important. It's the idea that if you have a path where the starting and ending point are the same, so x1 equals x2. So if you do such an integral over a closed path, and then you have a one form which is the result of a total differential of a real value function, then notice that this would be the function at the terminal point x2 minus the function at the starting point x1. But x1 and x2 are equal, right? Meaning that the function would evaluate at the same thing at, well, it's the same point, so you just get 0. So that's important, right? All right. Now there's other types of, well, related line integrals that look kind of like this. So the first one we want to talk about is the work integral. So we can define that as, we want to know how much work a certain vector field does as it moves along the path. But the only component, this is more like physics, right? But the only component of the force that will do any work is the one that's tangent to the path. So we have a unit tangent here. And in terms of a parametrization, the unit tangent can always be given by gamma prime, so the velocity, if you will. And then since it's a unit vector, you got to normalize, so you got to divide by the magnitude of the velocity, if you will. And so the only component that of the vector field that does any work is the component that's tangent. So we would project f onto the unit tangent, and that involves a dot product. Okay. So the work integral we can define is an integral over the path of the vector field dotted with the unit tangent times ds, let's say, like your book does. ds is just a differential length element. In terms of a parametrization, ds is equal to the, if you'd like, speed, right? So gamma prime magnitude times dt. If you'd like, this is like speed, instantaneous speed. This is like change in time. Speed times time just gives you distance along the curve. Sort of, right? Okay. So putting those together, we can have an integral over the path gamma. And we have, and by the way, our vector field has components, f1, f2, dot, 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 fn. Just like gamma has components. So now we're just going to rewrite t, the unit tangent vector, as gamma prime divided by the magnitude of gamma prime. And we're going to rewrite ds as the magnitude of gamma prime times dt. And then technically, I guess, we can now evaluate f along points on the curve. And the bounds would go from, well, let's say A to B. So again, t will be between a and b. All right. So notice that the magnitudes of gamma prime can cancel, and now we can write f, oops, f as a vector, right? So f has components. And then gamma prime, it's just where we differentiate each component of gamma with respect to t. And after we take the dot product, we recognize that this reduces to just an integral, right? One variable. It looks like the integral of a one form, in fact, right? It's f1 at gamma t times gamma 1 prime, and then dt, and so on. So this kind of looks like the integrals that we were just doing, and then times dt. We can also maybe more clearly see that this is really, you can think of it as an integral of a certain one form. So we can think of gamma prime t dt. Let's write it out. Here's the vector field. And then gamma prime t dt, that's just gamma 1 prime dt, gamma 2 prime dt, and so on, which we can then just think of as dx1, dx2. Okay. So this whole business here can be thought of as this dot product. So then it should be now obvious, painfully clear, that we have a one form. That's the work integral. So the one form we get is simply the result of taking the dot product of the components of the vector field f with, I guess what we're calling ds in the book. So what if this gamma is in fact equal to the differential of some real valued function f, little f? Okay, then the total differential on the one hand is the derivative of little f with respect to x1 dx1 plus, and we keep doing this, and that's equal to f dot ds, right? So that's equal to f1 dx1, f2 dx2, and so on. So what we would expect is that these guys are equal, these guys are equal, these guys are equal. And so the derivative of little f with respect to the ith coordinate should give you the ith component of your vector field, big F. Okay, and there's a name for that, right? So the vector you get if you differentiate some real valued function, little f, with respect to the coordinates x1 through xn. And I should write bigger, shouldn't I? Will be equal to the components of the vector field. And this thing, you already learned a name for that. That's called the gradient. The gradient of little f. Written like so, and that will give you your vector field. Okay, so in that case, the work integral, written as f dot ds, would be the same as the gradient of little f dot ds, right? And then this is nothing than, well, this whole thing is nothing but df. Okay, so in the case where your vector field is born out of finding the gradient of some real valued function, that's akin to saying that a one form is the differential of some real valued function. Okay. So then that just becomes df. And so by the fundamental theorem of calculus, this is just f at the terminal point minus little f at the starting point. And when a vector field is born out of finding the gradient of some real valued function, this function is typically called the potential, and this is called the conservative vector field. Conservative vector fields, you see, are path independent. The work integrals of conservative vector fields. And so the result just depends on the starting and ending point of your path. And this is from the fundamental theorem of calculus for line integrals. Let me check in on what's going on. Yeah, so let's look at an example of this, I guess, before we move on to Green's theorem and flux integrals. All right, so suppose we have a, all right, so suppose our vector field on R2 is 2xy and then x squared plus 3y squared. And we want to find a work integral from, I guess, 1, 0 to 0, 1, right? Okay, along some path of Sisyphus. I don't know how to spell Sisyphus. Oh my gosh. Or is it the other way? That looks better. Okay. Right, so here's our starting point in the xy plane. And here's our ending point. And we're taking the plane, the path of Sisyphus. Okay. Now, what you'd realize is that this vector field is born out of finding the gradient of some real valued function, so potential. So you can find what that would be because you realize that the derivative of f with respect to x has to give you f1. So that's derivative of f with respect to x is f1 here. So 2xy. So you can recover f by anti-differentiating with respect to x. We're treating x and y as independent variables. So this gives you x squared y plus some constant, except it's not a constant, it's a function of the other variable. And we know that's right because if you differentiate this with respect to x, this is just a function of y, so when you differentiate it specifically with respect to x, you get 0. And you just end up with 2xy, so that's the correct antiderivative. I can differentiate. Next, I would see that the derivative of little f, but with respect to y, should give me f2. So we'll differentiate little f with respect to y. And that's f2. So these x squares cancel, and you see that h prime is 3y squared. So h of y must be y cubed. So now you've totally recovered f. F is x squared times y plus h of y, which we discovered is y cubed. And that's up to a constant, really, but it doesn't matter. So if you want to do the work integral over the path of Sisyphus, you'd want to realize that f is the gradient of some real valued function. Okay, so according to the fundamental theorem of calculus, for line integrals at least, this is f at the terminal point minus f at the starting point. So here we get, yay, we get that the work integral is equal to 1. Right. Now, one way to, at least for a vector field on R2, if let's say we conventionally think of the coordinate components of the vector field being as p and q, if if our vector field is conservative, then we know that P is the derivative of some function with respect to x, say, and Q is the derivative of some function with respect to y. And assuming our vector field is smooth, C2, then if you differentiate P with respect to y, you need to differentiate Q with respect to x. By Clause's theorem, these should be equal. Okay, and if they're not, then your vector field is not conservative, right? So that's a nice test. So here in the previous example, we had a vector field where P is 2xy and Q is that one. Okay. And if you differentiate P with respect to x, and you differentiate Q with respect to y, well, something just went wrong. Oh, no, differentiate P with respect, differentiate P with respect to y. Okay, so that would be 2x. Differentiate Q with respect to x. And if these are equal, then there is a theorem that says yes, in a certain star-shaped domain, we know that our vector field is conservative, so then we can proceed to figure out our potential. So here's another example here's a vector field on R2, and it turns out not to be conservative. I know that because I did the test, right? The derivative of P with respect to y is 0, while the derivative of Q with respect to x is y. Those are not equal. So at least our vector field is not the gradient of some C2 function, some smooth function, little f. So f is not conservative. Our vector field f is not conservative. So if you do so if you want to do a work integral, you can't use the fundamental theorem of calculus, right? But let's say we want to integrate, do the work integral over the unit circle, counterclockwise. So if you wanted to do this integral directly, right, we know that we should be doing the integral over the circle of f dot ds, which is just p dx plus q dy at one form. Okay, and now to evaluate the integral directly, we need a parametrization for our circle. So we'll choose the obvious one. Gamma of t is cosine t sine t, and we know that that gives you counterclockwise orientation for the circle. And the parameter space here is to go all the way around. T has to go from 0 to 2 pi. Okay. So now we can evaluate this relative to the parameter space. So t goes from 0 to 2 pi. And then p, so p is x squared. And x squared will become cosine squared. Let me actually write it out one more time. So x was cosine, so we get cosine squared. Dx would be negative sine dt. Okay, and plus, then x times y becomes cosine times sine. And if y is equal to sine, dy would be cosine dt. So notice that these add to 0. So you have a definite integral of 0 dt. So that just gives you 0. All right, so now we know that if our vector field f were conservative, then this line integral over this closed path would have been 0, right? Here it just turned out to be 0. It didn't have to be. So for example, if we take maybe a path over, let's just say this should work out, right? Where this is, say, y is equal to x squared minus 1, yeah? And this would be 1 and minus 1. So let's say this is the line where y equals 2. Oh, no, wait a minute. Yeah, it's fine. Whatever, it doesn't matter. So this would have to be, let's just say y equals 3, right? So this would be 2 and negative 2 instead. That's fine. So if we took another closed path, maybe we wouldn't get 0, and like for this path we wouldn't. So the integral over gamma, the work integral, you'd have to break this up into two parts, right? Let's say C1 and C2. It's a piecewise boundary. So C1 is going to be this piece of the boundary. Let's say C2 is going to be this part of the boundary. So you'd have to integrate over C1 first. Okay, and so C1 can be parametrized, let's say, by saying that x is equal to itself. Y, however, would be x squared minus 1, as that piece is part of a parabola. So dx, let's just say x equals t. That way, yeah, y would have to be x squared minus 1. Dx is just dt. Dy is 2t dt. Okay, and the parameter space here would be t goes from negative to positive 2. And be careful of the orientation, right? We're going from left to right. So indeed, t can start at negative 2. And then plus, we'll do an integral over c2. Now c2 can be parametrized because, well, x is just, let's say, t. Well, it's not the same t, so just be careful. It's just I'm using t generically. And y would just be fixed at 3. So dx is dt, while dy is 0 dt, if you will, right? Because the derivative of a constant is 0. So in a sense, we don't have to worry about the dy part, because that's just 0. All right. So let's plug this in. And now in terms of the parameter, t goes from negative 2 to 2. We get x squared dx. And then plus x times y. So x times y times dy. All right, so what would that be? That's 2 t to the 4 minus t squared if you simplify. So let's see, I don't know exactly what this might be, but negative 64 over 5 plus 8 over 3 minus, wait a minute, I plugged in the lower bound first, so plug in the upper bound minus and then plug in the lower bound. So we get 2 times 64 minus 16 over 16 and all. Wait a minute, those are two different denominators. Well, I don't want to multiply this up, but you get some number. So this time, oh, we're not done, right? Because we have to do C2. Right, okay, well that's easier though. Because t goes, oh, well, t starts at 2, because x starts at 2, and then t decreases until t becomes negative 2. And that orientation is important because our bounds would go from 2 to -2. And then we have x squared times dx. And then since dy happens to be 0, we don't have to worry about that. So that's -16/3. Right? So at the end of the day, you have the number, the result of the integral over the parabola part of that closed path, plus the integral over the, so this is, well, I don't think this is 0, right? Yeah. Or is it? I sure hope not. No, it's not. Okay, this is not 0. So the idea, even though this vector field F, we did a work integral over a closed loop and we got 0, that does not mean it's conservative, right? Because it just happened the path we chose made it 0. If you choose another closed path, you won't get 0 necessarily. So, yeah. However, let's think about this. If you have a work integral over a closed path, vector field, and you get something that's non-zero, then is it possible that f is the result of finding the gradient of some real valued function? No, right? Or if you'd like another way of think of it is that omega, this is omega, is the result of finding the total differential of the f. Well, this is not possible because if it were the case, then we can use the fundamental theorem of calculus, and we see that we have the terminal and starting point are exactly, let's call it A, are exactly the same. So you would get 0, or if you'd like the other version of that. So the idea is that since we found that the work integral over a closed loop, we emphasize that, is non-zero, then there's no way that the vector field f can be conservative. Because otherwise that integral would have to necessarily be 0. Okay. So I don't know how much time we have, 15 minutes. Right, so let's look at, just as a review, not detailed stuff, but let's look at Green's theorem. So this is another manifestation of the fundamental theorem of calculus. So we have a simple loop here, a simply connected region, call it R, or D, I think your book calls it D, so domain of integration, I guess, I don't know. And it's oriented, and this is the boundary is sometimes written as using this symbol, like a delta for boundary D. So that's a curve, right? And it's oriented counterclockwise. So then if you have, let's write it this way first. If you integrate over that closed boundary, and you have essentially a work integral of some vector field, then this is necessarily the same as integrating over the interior of the region D. So we'd be integrating over the region bounded by, well, okay, I drew my region too large now. I wish there was a bucket fill, like in paint. Wow, color coding, amazing. Then you can prove that this is the same as the derivative of q with respect to x minus the derivative of p with respect to y. And just remember that p, just conventionally, is the thing that multiplies dx. And q is the thing that multiplies dy, alphabetical order, p, q, x, y. So that's Green's theorem. Where was I going with this? I guess an example. That's what I was going with it. And we'll later see that this is called the 2 form. and how to go from that one form to the two form fairly quickly. This is also known as, if you have a vector field, in some sources they'll refer to this as a two-dimensional curl. It comes from imagine the curl of some vector field in R3. The way you compute that curl is by curls, are these kind of cross product stuff is defined in R3. And you imagine that we have our vector field and we embed it in R3, so we have P, Q, and then the Z component of our vector field that we embed in R3 would be 0. And if you compute the curl here, you would get derivative of y of 0 with respect to y minus the derivative of q with respect to z. Now q is just a function of x and y, right? Because this vector field is really embedded is in R2, sorry, in the xy plane. So that would be 0. Likewise, the second component is 0, but the third component would be the derivative of q with respect to x minus the derivative of p with respect to y. And so this thing is what we see in Green's theorem, and that's why it's called the curl, because it's just a special case of finding the curl of a vector in R3. So it's also, we can also call it curl because of differential forms, but that's for another day. Okay, so let's do an example. So suppose you have a region in the xy plane defined by y being at least x squared and y being at most. So y equals x squared would give you a parabola. Y equals to 1 gives you a line. And we want to do the work integral of a vector field. So here's our vector field in our example. Okay, and so we want to evaluate over the boundary of D. Nah, I'm not going to highlight that. Waste of time. Okay. In Green's theorem in 1, your answer will be different by a factor of -1. We insist that that's a counterclockwise orientation. So we travel along the path this way. And we're integrating P, the work integral, right? So it's, here's the vector field. Here's ds. So we recognize that P, right, so you can recognize that this is the form P dx plus Q dy, where P is just the first component of our vector field, Q is the second component. But according to Green's, instead of evaluating this integral directly by parametrizing the parabola and integrating, and parametrizing the segment and then integrating, Green's theorem just says that this is equivalent to doing a double integral over the region that's bounded by the boundary. And then we have the derivative of q with respect to x minus derivative of p with respect to y, dy dx, or some differential area element. Okay. And there we go. Let's compute the derivative of q with respect to x, and then minus the derivative of p with respect to, oh, wait a minute. This is supposed to be minus. I feel silly. Sorry about that. So the derivative of p with respect to y is -1/2. So indeed, if you noted, you get 1 in dy dx. So this would give you area of that region D. And this is actually a beautiful, beautiful thing here. If you integrate this one form over the boundary of some region, then this integral always gives you the area of that region, right? Because according to Green's theorem, you always get the 1 here, derivative of q with respect to x minus the derivative of p with respect to y gives you 1. So this always, just by definition, gives you area. Interestingly enough, right, I guess if you run around something and you take careful notes, you should be able to deduce the area somehow, right? Okay. But I guess if you really wanted to integrate, x would go from -1 to 1, y goes from the lower bound of x squared, y starts on the curve where y equals x squared, and then y increases till it hits the line where y equals 1. So you get 2 minus 2/3. Yeah. So 4/3 is the area. All right, well, I was going to go into something related to a work integral, but I think we have 4 minutes left, so let me just, for next time, I guess. Right, so if you have a vector field in a path, you can always find a unit vector that's in the direction that's tangent to the path, and another vector that's perpendicular to the path, that's perpendicular to the unit tangent, and outward pointing as well from the interior. So what we've talked about is an integral of f dotted with the unit tangent times ds. Yeah, or if you'd like, it's f dot ds, the differential vector quantity over that path. So we call these work integrals. But maybe the physicists might be interested in the integral of f, but in the direction of the normal. It's perpendicular. So f dot n, unit normal vector, ds. All right, now let's just take a basic example. So if we have a parametrization of a path, and this is gamma prime, the unit tangent can be the tangent vector divided by its length. Now the unit tangent vector, or gamma prime will have components. Say this would be a gamma 1 prime, this is gamma 2 prime. What we want is an outward pointing normal. So we can kind of reason that something that's perpendicular to t prime would be, well, you would make the x component negative, and the y component, wait a minute, go backwards. So the x component would be gamma 2 prime, and the y component would be gamma 1, negative gamma 1. Indeed. Right, gamma prime is gamma 1 prime, gamma 2 prime. Dot that with this new vector. And if you take the dot product, you get 0. So these are necessarily orthogonal, and this also has the right orientation. So we'd say that the unit normal is minus gamma 2 prime. And then for the second component, plus. And the second component is minus gamma 1 prime. And it's a unit normal, so we're going to divide by the magnitude. All right. Well, it's 3:15, so I'm going to continue this at some other time. Let's see if anybody's here. All right. Well, thanks for joining. Well, let's just give this a name. Let's finish this. Geez. So here's F. Some parameter space A to B. The unit normal is, let's just say F has components for F1 and F2. Right, and then we have the components of the unit normal. So that would be gamma 2 prime, gamma negative gamma 1 prime. And ds we know is the magnitude of gamma prime dt. So these cancel. All right, and we realize that this is, since y, or if you like x2, is gamma 2 prime dt. Sorry. x2 is gamma 2, right? So dx2 would be gamma 2 prime dt. So this is f1, let's just call it dy, actually, minus f2, and this is going to be dx. If x is gamma 1, then dx is gamma 1 prime dt. Over, and we're integrating, let's say, over, so that's a flux integral. Now, if you're doing a flux integral, so flux in physics, so if you have a flux integral over a closed boundary, then we can think of that as minus f2 dx plus f1 dy. And so Green's theorem might apply here, right? So we think of this as p dx plus q dy. So according to Green's theorem that I'm using here, it should be the same as the double integral over the enclosed region D. And Green's theorem says that this should be the derivative of q with respect to x, the derivative of f1 with respect to x, minus the derivative of f2, or p, sorry, p. So the derivative of p, where p is negative, f2, with respect to y, dy dx. So get a plus over here. And so this expression is called the divergence of the vector field F. So the divergence of our vector field F, written also as del dotted with vector field F, would be the derivative of the first component of F with respect to the first coordinate plus the derivative of the second component of F with respect to the second spatial coordinate, and so on. If you higher dimension, you just keep doing that. So this is called the divergence theorem, right? So Green's theorem also gives us divergence theorem in the plane. There's a divergence theorem for higher dimension, right? Well, I didn't have time to, we don't have time to do an example here, so we'll maybe do that next time, add it in or something. But thank you.